Welcome. A kind of technical notes I discussed last week with Professor Elsner, and with respect to this plan here that I summarize in this graph, I will. So we decided I will also talk a little bit about machine learning interaction potential. So standard abbreviation in literature is MLIP. That are mostly, at least the modern generation, are graph networks, or specifically message passing graph networks. Yeah, so I put it here under descriptors because at the end of the day, the most of the story is about which descriptor you choose to represent your coordinate and the system, and then yeah, it falls back into the graph network thing. But yeah, I mean, it's not clearly not a minor point in the overall research, but yeah, okay, I will try to give the important things, because if one goes into all the possible potentials, strategies, yeah, it's could be a full course. Okay, so today I want to recapitulate. Lost my pen. Yes, the previous lecture. So in particular, the point, general point about what is a perceptron as a constituent of artificial neural network. Then the point that a neural network is a universal approximator or classifier, according which kind of property one is modeling, and then there are severe challenges when trying to train a neural network, and then I will essentially address how we do first the general algorithm, the so-called back propagation, and then also some extra tricks that people use in the field for doing actual yeah, efficient training of networks. And then yeah, depending where I arrive today, I start introducing convolutional networks. Okay, so the idea is, so last time we introduced the perceptron. That is the constituent of a network, and the general setup is that we have a kind of unit that accepts many possible inputs, and makes the linear combination. So there are weights. Say this would be the weight 1 combined with x1 plus, so linear combination of this. Okay, sorry, sometimes it gets frozen. Yeah. So wnxn, right, and then we have a nonlinear unit. This step symbol means that at least in the original formulation we have something like that y is 1 when z is bigger than a certain threshold t. So let's say that here this, and 0 otherwise. So to zoom in, what is in the means that we have an input that is the output of the previous unit, and then we have a threshold, and then we have our activation that goes like this. And so it is still interesting to look into this original setup this is from 1958, guy called Rosenblatt. The interest is not just historical, it is lays in the fact that every modern neural network is a combination of these perceptrons, also called artificial neurons. Even though we have some couple of extra tweaks. First of all, well, we could embed the threshold here with some bias, let's say, so that we have something like that, so that we have then the kind of activation function that is always centered in 0. So basically the threshold goes into a bias. So the linear combination becomes a so-called affine transformation, just because there is an offset. And so then the other relaxation or the other evolution is that this step function actually becomes smooth, addressing actually one of the issues that we'll mention in a second, but I mentioned last time, so just as a summary. So we have now a smooth function that could look like this, so something that goes between, so this is still 1/2. So this is a logistic kind of function that looks like, if this is z, if this is y, you would have that y is equal. So it's exactly the same model function that one has in logistic regression. That is a way to describe a classification problem as a regression problem, in the sense that instead of just having 0 and 1 as output, you have values between 0 and 1, and then you can assign probability to actually be one in one or another class. And then, so this is would be one modern incarnation of the step function, and the other famous one is the rectified linear unit. So ReLU. There are several variants of this one, not so rectified, like you would have some kind of smoothing of this part here, because one may want to avoid the kink in the origin, but the original, well, yeah, there was necessity to introduce this activation function that looks a bit weird with respect to the step. I mean, one can easily understand the logistic as smoothing of a step. This one does not look like too much as a step, except that, okay, you still have the output is completely 0 below a certain threshold, and then it is the input itself. So say, for example, I'm not aware of any variant to the fact that is really y equal x or z, so y equal z in. So there is no need to have another slope there. Right. So this would be the basic constituent of our neural network, yeah. So neural network means that we combine many of these neurons. So now, if we have let's say now I basically combine, maybe change color, make it more clear. So if I put together this node, I would have inputs and an output, and inside we have the overall transformation, and so we can combine more of these nodes, where, to be more specific, typically we have that there is a kind of input representation, and then there are weights that go to each of these neurons, something like this, and then each neuron will have its own output, and this kind of architecture would be prone to treat a generalized classification problem or regression problems. For classification, probably I should move a little bit down. We have, say, any input that, of course, on a sheet or board is always two-dimensional. So in general, the classification would be finding areas in our input space that are classified as somewhat positive, and everything that is outside these areas is classified as negative. Generalizations to multi-class can be done in a second. And the idea is that each neuron, so let's say if I focus on one of the neurons in this network, could be such that it will classify one edge of this, say, complex polygon, and then there would be another neuron that would classify the other edge. So then you would have neuron red, neuron, so green and red, and then the other neurons for the other edges. The input is always the same, so it would be x1 and x2. The weights that go here, so this would be, say, weight 1 connected to input 1, weight 1 connected to input 2, and this is the neuron 1. Would just be something related to the slope of an intercept of this particular dividing plane, and at the end the information is combined, say, with a end kind of neuron. An end kind of neuron would have something that has so the weight is fixed to 1 for each of these branches. And then you need that, you have to reach, say, 5 in order to get a positive classification overall, right? And so I go a little bit into detail here because essentially one can rigorously prove that any classification problem can be recast in this kind of sum shape for which I have a boundary. Doesn't have necessarily to be convex. So if it is not convex, one can divide it into convex region, and then you have a kind of a final end. So the rigorous proof says that a neural network with one hidden layer, so basically hidden means that there is something in between the input and the final kind of decision layer, it is a universal approximator. Actually, I should also, as I did last time, kind of, it could be interesting to see that if you say now my classification is this one, I have, say, a subnetwork that first of all tries to see if I am inside, say, the pentagon, and then I have another subnetwork that tries to see if otherwise we are in the square. So then I need only 4 dividing planes. The input is always the same, right? So I just have points somewhere in this plane. So well, I don't like right here. And then I have a final, so this would be an end, and then I have a final or, right? So I am either in the pentagon or there. So this kind of network is a universal classifier. So any possible partitioning of the input representation can be captured, modeled by a network once you put proper weights on your nodes, on your in the connection between nodes. So when we think about regression, it is the first time I found it bit of underwhelming because the network is actually doing a classification. So basically it is basically partitioning. So let's say if we have a one-dimensional kind of problem, we are binning essentially our function between the threshold 1 and the threshold 2, and then say the basic unit would be something like I have an input x, and then I have some so basically I have something with threshold T2 and T1, and so I get a signal if I am I pass the I am after T1, I am before T2 because there is a minus here. So and then if this is passed, then there is some kind of so the height of this is the output of this end. So you have to tweak a little bit the definition of end. Instead of just having 1 or 0, you have a number h or 0 if you are not there. So the kind of basic element of a regression type neural network would look like this, and then if you combine elements like this with the OR kind of neuron, you would map all the possible values. And if you go to more dimension, essentially, so the input would be x1, x2, and then the output, it would be eventually a set of cylinders like this, right? So the network would kind of sense whether it is inside a certain cylinder, and then it will learn the height of the cylinder, where imagine any function of 2 inputs that can be decomposed in this kind of cylinders. Yeah. So, I mean, this is at least the way one constructs the proof that, again, a network of perceptrons with at least one hidden layer would be able to approximate any possible function. And then, of course, the unpleasant thing that essentially you are mapping a possibly continuous function into a piecewise kind of constant function. That means that it's in this particular way, if this interval is finite, you would destroy the smoothness, so it would not be differentiable and so on. So that the part, even though originally with the step function, still people would do this kind of regression and would not bother too much about the non-smoothness. The moment you have a smooth activation function, you recover all the smoothness, right? So essentially, it is similar. So you express your function as the composition over a basis set that looks like this kind of activation function in different places, right? So this is more the justification that the network is a universal approximator and regressor. Then I was mentioning issues, training issues. Say issue 1 is that we do not actually have the correct training data if we want to directly train, say, it is easily seen for a classifier, in which we say if we want to model the classification of being inside this polygon as a superposition, so as a end logical operation over the different hyperplanes, I need to know for each of the perceptrons, so that makes the decision, whether we are say in this case on the right side, upper right, or on the left of that perceptron. But our training data actually just tell us if we are outside or inside overall the polygon. So we would need to have an algorithm that goes from the original problem to a specific classification for each of the perceptrons. So that's immediately says, yeah, in principle you can, but in practice you would need to prepare the data in a very inefficient way, because as soon as you have an actual problem, you will have issues in labeling the data in that way. So probably just passed in the back of my mind. So this classification kind of problem. So in general, the fact that we map a classification problem into recognizing shapes in some space is still general, right? So even if we want to recognize any kind of pattern in an image, or label an image of any kind, or any possible set of input data, one can always recast that classification into a linear classification under certain conditions. The point is that the network, as I will show, will learn which is the specific representation, so that you have at the end a linear classification problem. So it's not that, I mean, the universality is really universal. It's not that we need to have a composition of linear problems from the onset. It can be always remapped into that. So that this is a serious issue. And then we have another one that is issue number 2, is smoothness, essentially. Smoothness in error. meaning. So let's use the same example as last time. So if we have a classification problem, and at some point in our training, we are, so the ideal classifier will be, say, here. So we have here only an input. I'm just saying that the class here is 0 or 1. This would be the output, right? So the solution of this classification would be some threshold like the one I plot here in green. And at some point during our training, let's say we land with a classification that is more, let's say, here. And then we say, okay, a good measure for how bad I am is to count how many points I have misclassified, and then here would be this 3. And the issue, so the smoothness in error issue, is that if we move by a small amount this boundary here, until we don't hit one other point in our training data, we have no information whether we are doing better or worse, right? So we definitely need, in order to have a kind of universal or robust, at least, training mechanism, that we know if we are going to the left in this case, we are improving a little bit because we are getting close to classify better one of the points, or if we go to the right, we are doing worse. So we need to define an error that it is smooth. And so this leads me to definition of error. So for, let's say, regression problem, we would have, say, ground truth. I try to always use G for ground truth, and then a function that tries to approximate the ground truth. So this would be example with only one-dimensional input, and we are fitting the function. So a sensible error would be, say, defining as a function of position x the absolute value of x minus g. Absolute value because we don't want that the error cancels, because at the end we want to define an overall error for a function that it is the integral over all domain of this delta x in dx. So this would be the formal definition. Well, it's not, it could be even operative if we knew f and g. So we can define, we can calculate this integral, and it's well defined because at this error, in this case it would be a function, so it's called the loss function, would be 0 if and only if f is coincident to g in all space, because every discrepancy would result in a positive deviation from 0. So it will be some positive error. I said, yeah.
So the red line here is f of x.
Yeah, sorry. Yes, it's yeah. I'm thinking if I use more f or more y in the following. Yeah, f. That be, but definitely yes. This is the function that we are. So this is f. Perfect. And so this definition has little practical use because it would require to know g. At least the analytical expression is g, but we are fitting g, so that is just a formal definition. So in practice, what we have are instances of f and g, observation. So our data points would, we need to know what is G for those data points, and then we compare to what is the prediction of F. So we now define delta I, that is the delta at specific positions I, and then it's it's Fi minus Gi, and the overall error would be just the sum of the delta I. So similar, so consistent definition, and this is typically called empirical risk, and we want to minimize these empirical risks. So we want to phi F such that the empirical risk is as small as possible. Right, so that leads me to a more precise definition of our training problem. That is, if we have a function F will be a function of some parameters W and the input. So our training would be the finding the W such that this empirical risk that is a function of F, that is a function of the parameters, and the input variable minus G of X. That's it. So we are looking for parameters such that the empirical risk or loss function, also another name, is minimized. Yeah, I mean, there is a small difference. The loss function is the analytical definition. The empirical risk is when you project it onto the data, so you discretize this loss function. Okay. So I will not repeat the how the kind of gradient descent solution comes in, but I just write down that eventually what we construct is a sequence of parameters. So our training will actually be a sequence where the next in the sequence is the previous minus something that is proportional to the gradient of the loss function with respect to the parameters themselves, right? So this is bigger than 0, and the idea is that if we move in the direction of the gradient with respect to the parameter themselves, we typically move downward. So if this step is small enough, we are guaranteed that we go downward in L, right? So if we choose another set of parameters such that we do a small step in the direction of the gradient, we are going to a set of parameters such that the loss function will be smaller than the previous step. So this is the basic idea. So this is gradient descent, and it turns out that with only a minor kind of well, not so minor, but with some tempering of the actual definition of this gradient and that parameter that is actually known universally as learning rate. So whenever you hear about learning rate in your training of neural networks, that is eventually related to that positive coefficient in the gradient descent. So with some tweaks, but the general mechanism is always the same. So any neural network, from the simplest to the most to the biggest language model, it is trained with this basic machinery of gradient descent. Now, before I go into actually how one can evaluate these gradients with respect to the weights, to the parameters, and yeah, the W's because they are typically called weights in a neural network, right? So this, oops. Okay, it's shown here. So everything that it is in the affine transformation is called weight. So before that, let me talk about a little bit what we can expect to have in X, in Y, and connected to that what we have typically in the loss function, right? So input representation, as I've shown, well, not very much, but every time I just say, okay, there is a x1, x2 that enter my network as input, then the first step would be, where is it? Yes, here, for example, you take a linear combination of this input and then take a nonlinear transformation, and then if you have more neurons, each of them makes a different linear transformation because the weights will be different. The same nonlinear transformation, typically you could have every neuron to have its own activation function. Never happens because it's already general enough in that way. So, but that means that X is basically very flexible and versatile. So you could have any so X, any set of scalar values that could be completely conceptually uncorrelated with each other, right? So you could have, I characterize my data points, if it is a person, you would have, it could be a scalar and also classification, like, yeah, whatever, integer values or something like. So you could have defined the gender, height, weight, and any number related to that person could be an input to the network, and not bother very much, because in principle the network can deal with any kind of heterogeneous input, right? So you might then think what it means to make a linear combination of gender and height, but it doesn't really matter. So it's just some machinery for the sake of the network itself. But then it could be any kind of set of numbers that actually have some correlation, meaning, for example, you have a spectrum, right? So you have any kind of spectrum that you measure as a function of any physical variable, and you could give just the discretized version of this as an input. And you see many examples of network where people just analyze spectra by just using the intensity in each bin as an input. Could be a time series. Okay, let's write down spectra. Any type of time series. Right, so when now our x1, so x2 would be at the later time than x1, and so on and so forth. You could treat that with a network as simple as the one I'm describing now. there will be smarter way that I will introduce, but it could be anything like that. And then you could add dimensions, so it could be an image of any kind, so anything that would be a map from 2 dimensions to a 3rd dimension, so it could be like a picture, so from a bitmap, so from pixel to intensity or 3 colors intensity, to any kind of possible representation. So you do not need, especially in this basic setup, that I mentioned last time, but I didn't. So this would be the setup of multi-layer perceptron. So MLP. Oops, no, I should never do that. Okay, let me write again here. So multi-layer perceptron is so the abbreviation, universal abbreviation is MLP that you find everywhere in literature. It would be also a synonym of fully connected network, where the full connection is really that you have weights that go from every node of one layer to any node of the next layer. That's the full connection. You never have connections that skip nodes, skip layers, not in a multi-layer perception at least. And then, yeah, text. That could be also text. Typically, you need to transform the text into some kind of vector, because now giving letters as an input is not so treatable. But besides that we will really look, because this is the beginning of a language model, will be your X. The Y, the output of the network, is very naturally so some number that is in so it's a real number that is the very typical case for a regression. So you see, you enter, so you do your transformation, and then you have your output with the smooth activation function, and that would be naturally a number. So if we are predicting a scalar, that's perfect already. If we want to predict a binary classification, unless we construct some kind of network with the only 0-1 activation function, but that we don't want, because we will have problems in training them. What we have is actually a probability. So we will have a continuous number, a real number, and we can interpret it as a probability to get a certain value. So 0 or 1, because it is a binary classification, given the input. So to be a probability, it means that we have to manipulate the output such that it is between 0 and 1, and such that, yeah, the probability to give 0 is 1 minus probability to give 1 in a binary classification. So we have to normalize the probabilities. And this is, do we see it now? Yes. So if I go directly to the multi-class classification, we want to interpret the output as a probability to be in a certain class, given, yeah, I should put correct. So given the input. So what the network will learn are numbers, and we want to interpret them as a probability. So a network that does classification over multi-class will have essentially a final transformation of the output that is inherently a real number. We'll have the so-called softmax transformation. It means that every output that would be a real number y is transformed in this way. So you take the exponential of that and sum over all the other possible outputs. So this would be my capital Y. So if I do this kind of transformation, I am guaranteed that I have numbers between 0 and 1 and the largest, so they can be interpreted as probabilities, and then yeah, so it would be a generalization of just taking, say, the largest of all the y's as probability 1 and all the other 0. So we want to give some interpretation of outcomes that are not exactly 0. Yeah, there are several justifications why exactly there is an exponential here. Nothing is how to say necessary. So it is like people started using this one. Of course, it's intriguing that it looks a little bit like a Boltzmann factor, and indeed there are easy variation in which one puts some kind of temperature there. So, but I don't want to go too much into that. So, in one way or another, whenever you have a classification problem, there is an outcome of the network that is just real number, and then there is a softmax layer that transforms them into proper probabilities. Right. Then in your training, you will just have that something is either correct or not correct. So correct. So you compare that number that would be a number between 0 and 1. It would be correct. So there will be no difference from the actual result if it is close to the correct class, or otherwise you get some signal. And this leads to the next point, that is how I define a loss function. So I should say that for essentially any step that I mention, from certainly the activation functions to now how we define loss function and so on and so forth. Like the softmax here, there are a lot of variants. So I hope that I say enough that if you go to any literature in which people are using some tailored activation function or kind of transformation to get probabilities that is not softmax, is still understandable, because it would be pointless to go through all possible. All possible would be even probably not doable given the amount of papers that are published per year in the field. So also for the loss function, we will have many possible strategies. So loss, where do I have it? X, Y, and then loss function. So for regression, I'm sure you're not expecting that the most used loss function would be the mean square error. So basically, or the squared error. It doesn't have to be mean, but for practical reasons, you average. So it's defined as now. Okay, let me try to use f minus g. Norm 2 squared. So that means that in practice we will have the sum over our instances g of I squared, and yeah, as everywhere in physics and statistics, the 1/2 is there because when we take the gradient with respect, in this case, to the f, input. So basically we want to see if we change a little bit the output of the network, how much our loss function will change. So that would be exactly f minus gi, because then the 1/2 simplifies with the square in the derivative. Now a little bit less obvious is a proper loss function for classification. So I was saying that the most used, I would say, probably is a tie between the Kullback, Leibler. I hope I have to check every time if it's correct. Universally KL. Divergence. So the other one, I will not write down the other one because it's a kind of minor trick with respect to the Kullback-Leibler, but you find it expressed, used a lot, is the mutual information. But it's just a minor difference between the two. So I will just express one. So there is no how to say, strong argument to prefer one to the other. It's essentially the same for all practical purposes. So this KL divergence is defined as the dissimilarity So just a note, people use the word divergence, and then I will use dissimilarity to avoid to say that it is a distance, because it is not a distance, so because it is not symmetric. But let me just first say what it is, and then I can comment a little bit more. So it will be the dissimilarity between the actual distribution that we are measuring. So let's say if it is a binary thing, we will see y and 1 minus y as possible outcomes. So our distribution in the outcome will be y1 minus y for the input. Dissimilarity between this and the expected one. So we will have a kind of I use q. Okay, so this is what we would like to have, and we are comparing to what we get, and it is written in this way. So it's KL is equal to there is a minus, yes, minus q log y minus 1 minus q log 1 minus y. Yes. For binary, and for multi-class is now the sum over all the classes of this. So you have a QI for each of the class that you expect, and then you compare to what you actually get. No, yeah, I managed to make it the opposite. It's QI minus over y. And essentially, typically so except for few cases, the expected distribution is 0 everywhere except for the right class. So that would be a sum of things that have zeros in the QI, except for one class where it is 1. So that means that this is always minus logarithm 1 over the correct class. So this is actually our KL divergence for a multi-class problem, and takes a little bit of algebra to show that the gradient of this KL is 1 minus Q. So, and this explains, so basically it's constructed backward in order to get a gradient that it is reminiscent of the regression kind of problem. So at the end of the day, we have always the discrepancy between the actual value and the expected value is our gradient. So okay, so this is now a little bit of general description of what we have as input output and therefore possible loss functions. Or conceptually, of course, we could have many different loss functions. But as we will see, we need something that is we can treat easily the gradient. So you need a loss function that is smooth with respect to the input, certainly. Okay, let me go to the and the reason will be here. Where are you? Sorry. Here. Oh, okay. Managed to make it even more complicated. Okay. So, training. So, as I was saying, we are looking for the set of parameters or weights that minimize the loss function. It is a function of the weights and the ground truth. So what we do is that let's say following gradient descent, is that we say, okay, let's start with the zero weights or random weights. There are some prescription whether it should be zero random, but let's say for the sake of this presentation, it's just start from somewhere that is zero. And then we say do this update, the weight at iteration +1 would be the weight at iteration 1 with the gradient descent update until our is that yes. So now as a function of the weights, so basically we define a convergence criterion, right? So we iterate the gradient descent until the increase of so the decrease of the function with respect to the previous step goes below a certain prefixed threshold. So basically we are not improving by doing the following the next iteration. So yeah, here I have my nicely drawn network somewhere up there. Yes. No. Okay, I have to take it as a block. So if I have a general network, let me explain a little bit the notation. So we have So the neurons will, each neuron will have first the affine transformation. So basically we have a linear combination of the input from the previous layer, and the what was the threshold in the perceptron, or whatever constant that you have in the transformation is typically absorbed into the input from the previous layer by this one block, meaning so this common trick in linear algebra that you express the bias as just a one, and so that you learn now a weight that learn any kind of bias. So the Z1 is linear combination of the input plus a bias that you can see as a constant one input multiplied by the weight connected to that particular input. So you do this. The kind of the input to the neuron would be this transformation, and then you do the nonlinear transformation. So the Y is always the nonlinear transformation. So the activation function applied to one to the input, and almost everywhere you will find Z as the outcome of the affine transformation, and Y as the transformation after the activation function. And then, yeah, of course, the index here above is the layer 1, layer 2, layer 3, and so on up to layer n. And here you would have the final outcome of the network, right? Y at layer n is what we see, and this is what we basically, so our loss function would be now yeah, so it would be the Y at layer n minus the ground truth, right? So the what comes out from the last layer of neurons is our output. So capital Y, meaning so it's a collection of all of this. So Y is a vector of Y1, Y2 at the last layer. Yeah, and then often for simplifying the notation, the input is just the layer 0 Y. So okay, so this gives the basic architecture, and if, let's say, for any given set of weights on this network, we can calculate the output Y by just iterating. Say you go. Okay, let me just to be sure I used correct notation. So we are iterating over layers, and then we are iterating over nodes in layer or neurons. So this would go to the dimension of each layer. So each layer K would have a dimension D, and we cycle over all the neurons, and for each of them, this is like a small letter. We calculate at layer K our and then that's why I don't. Okay, let me change on the fly. This is activation function of Zj. Okay, Z of K the activation function in principle could have indexes. It could be different for each node, it could be different at each layer. In practice, I've never seen anything like that. So then we do without any index. So worth noting here is, so we have the as an input to calculating the z, so the outcome of the affine transformation is the output of the previous layer, so k minus 1. This includes the bias, so there will be this 1 here, and includes also the first layer. So when k is equal 1, you have the y zeros here. So one calculates this for all the layers, and when this is done, output the vector y, that is y1 at layer n dot dot y dimension at layer n and then evaluate the loss function of y and g. So we can do this operation given the weights. So at this level, I know the weights, and this overall thing is called the forward pass. That of course, is what also we use to when we use the network for the training network for evaluation. So we do exactly the same once the weights are fixed. And then now, since we want to evaluate the gradients of the loss function with respect to the weights, we have to work a little bit keeping in mind the architecture, right? So we want the gradients of the loss function, and let's say via what we can easily, or what we can calculate step by step, are the gradients with respect to the inputs, so to the outputs, the gradients with respect to the z's, but essentially this is what we have, what we can calculate, and we have to build to construct or better compose the gradients in order to get what we are actually after, that are the with respect to the weights for all layers, right? And to do that, we do the so-called backpropagation. And we start saying point 1, that we can calculate the derivative. So I will use the delta. So the delta, I remind you, is the error for one specific data point. So we can evaluate the derivative with respect to the z. First of all, we write it by the chain rule. So the whole neural network business is iterative application of the chain rule. So, oops. delta. Okay, right, so we want to write the derivative. So how much the loss function changes when we change the, say, the z here at the layer n. So that is, well, should have put n here. So that, so this is a mathematical equivalent. We just expressed the derivative as a composition of two derivatives, and so we know this one, meaning that we have the output, so we can calculate this derivative. It was a regression, just to remind, it would be the y minus the ground truth for that particular instance. And this expression here is just the derivative of the activation function, right? So here we have that y is kind of alpha z, so this would be alpha prime of z I n. So essentially, when you set up the network, if you code manually, of course, you will typically use a library, but what you have is the activation function and its derivative. It's part of the, so you just evaluate that thing. So this would be one step of our back propagation. Then we go one step below, so we want to now evaluate, here we have the weights of layer n. So one step backward would be, now we want to evaluate the derivative of the error with respect to the weights. And this is also chain rule. Right, and it is written in this particular, so I need to put all the indexes, otherwise it's pointless. So for the layers, and then we know, so this step is from the previous evaluation, so we already know this one, so I will just rewrite it as it is, t delta dzj. And what is this one? So well, we know that the z are, it's always a nightmare with the correct indexes. Plus all the others, so this would be just, so the z at one particular node would depend on all the weights and all the previous inputs, but we are interested only on the derivative on one specific ij. Why did I write this here? This is ij, sorry. So we would have all the rest here, but when we take the derivative with respect to the wij, we have only yi n minus 1, right? So here I have yi at n minus 1. Last step, because then everything repeats recursively, is the derivative with respect to the input in the previous layer. So now we have this is summed over all the j's, right? And the zj is again yij yi summed over all of them. When I take the derivative with respect to the yi, we get yij, right? So this derivative is sum of yij d delta dzj. Okay, so that's the end of this. Okay, now I need to also, so this one is also the same here. So I can express the derivatives with respect to the z, to the w, to the previous output as products of quantities that I know, right? So I know this one I know from the overall output, and then I multiply by this one, and then I compose, and then I multiply by the previous output, and so on and so forth. So I can construct this this gradient so that in practice we initialize the algorithm, back prop algorithm starts from the last layer, so we definitely can evaluate the derivative with respect to the output. We evaluate the derivative with respect to the zi at the n, that is, I use alpha now, of the zi at that layer, d delta, dy at the last layer, and I calculate the yij so here I have already used the results from this analysis here, right? So I have the derivative with respect to the weights are already the previous output times these guys here that I have written here. And then I iterate the following, right? So I say for all layers, now we go backwards, right? So until the last layer, we go over all the nodes in each layer, or neurons, and we evaluate the derivative with respect to the eyes at layer k, okay, as we can evaluate this derivative by knowing what happens in the previous step, right? So in the previous layer. So this one we have evaluated for the nth layer, so we can evaluate this at the n-1 layer, and so on and so forth. And then we evaluate also those ones. No, I changed the nomenclature. Z. Okay, and then I just cycle over all also the j's in the previous layer in order to take the derivatives of the Yijs. So I'm spending time here because this is the basic algorithm that shows that so it's called backpropagation because you propagate the gradients backward, right? So at each layer you evaluate the basic quantities, the derivatives with respect to the outputs, to the input, to the activation function, so the z's and the weights themselves, and we can construct. So what we actually store are these ones, right? So what we need are all the derivative with respect to all the weights, because then at the end we evaluate our beloved W. At the next step is the W minus eta gradient of the W's, right? So we need to know exactly for each weight in our network what is this gradient in order to do that. So this is our overall step. So so algorithm. Now a few remarks. First of all, this algorithm is pretty robust, but there are a few caveats. So let's say but there has been a lot of analysis of this steepest so gradient descent algorithm, and people were happy always to find counterexamples where this algorithm is particularly bad. So let's say that you have a simple learning, so that you will never do with a neural network, but you just classify these points and you want to find the dividing plane, right? Something like that. Okay, you say that you have found it. Now let's say that you complicate only slightly the problem, and you add one extra training point, but this is devious. So this is a point on exactly on the same axis as the point above here, but it is actually very distant from the other points. Now, people were until a certain point quite happy with the perceptron. So the perceptron algorithm I mentioned very quickly last time will find the exact solution for this classification problem, even starting from this one. So you just add an extra point, it will say, okay, I have to now classify this extra point, it will find this solution. The neural network, so the gradient descent, if you apply only to one neuron, will not find the solution, because essentially if this point is far away, the change in loss function when you move a little bit this dividing line becomes negligible. It's basically it will be small respect to your criterion for stopping. So this is clearly the extreme case, but what is the message here is that the neural network backpropagation. Okay, so I should say that at the same time it gives some robustness to the algorithm, because basically there is no need to move the dividing line for the algorithm, because the loss functions doesn't change enough to justify that. While if you have an algorithm like the perceptron algorithm, actually you will have different solutions that are available. So the backpropagation algorithm has low variance, low variance, yeah, but the bias is a question mark, because it could be that it doesn't find the actual solution. While other algorithms, like perceptron algorithm, in contrast, would have low bias, so they will find the exact solution, except that they are more fragile, right? So they will react to small changes in the input data. So this is good, the good and bad the gradient descent in back propagation is that it has so the good is that it has low variance, but it doesn't guarantee to find the global minimum. Then there are a lot of other interesting properties of multidimensional surfaces. So one can easily prove that actually such a surface, I mean, the way it is constructed for neural networks has mostly saddle points rather than local minima. So it's somewhat easy to formally demonstrate that you will have a lot of locations where almost all the gradients, the direction of the gradients will vanish. All the derivatives, all the partial derivatives will vanish except for one. So you have a lot of saddle points, and then of course that's not a minimum, but this algorithm will tend to find all these saddle points. But now, yeah, before I close, let's say that the basic algorithm, as I was saying, is this one. So the steepest descent, but there are some interesting ideas on how to, first of all, choose this learning rate, and also how to tweak a little bit this gradient, even though we do not want to calculate other things than the gradient. We can use the information in the gradient a little bit in a more clever way. So I will do that next time, but let's just introduce the convergence kind of general problem. So if we have a nice convex function, we calculate the gradient, right? So we know that we want to go in that direction, and then we have a certain choice for this learning rate. So we will move in the direction of the gradient, that will be this direction, by a certain step. So to fix the ideas, if this is not only convex but quadratic, so it's really can be modeled by a parabola, we actually can calculate what is the so-called optimal learning rate. So this is so this is Newton method, is actually 1 over the second derivative. So basically we can evaluate what is so this is the learning rate that guarantees to find the minimum in the smallest number of steps. It will not be quadratic, so you can approximate, but I'm saying this because we see what appears here is the second derivative. So typically we don't want to look into the second derivative, especially because for a multidimensional function that second derivative will be the Hessian metric. So that would have, so you have a function of as many weights as you have in the network. If you take the gradients, it would have as many components as the number of weights. If you want to look into the Hessian to evaluate the optimal learning rate, it will be the square of the number of weights. And since we are so happy to have networks with thousands, if not millions of weights, the square of that becomes not treatable, and so we never do that. So there are ways to kind of use the information from the gradient to evaluate, to speed up a little bit the optimization. And I close with just so from this optimal eta learning rate, we have 3 basic situations. So we have the situation in which we use an actual eta that is up to the optimal. So we have guaranteed convergence if the function is has a minimum somewhere there. So I mean, it can be approximated as a, so it is convex. It just has to be convex. Sorry, let me complicate too much. But just for the sake of understanding, we have a situation in which if eta is in between the optimal learning rate and 2 times, we have the so-called jittering. So basically, we still have guaranteed convergence, but we will bounce back and forth across the minimum. The problem is that if eta is bigger than 2 times the optimum eta, we have, so this is jittering, we could have divergence, right? So we have a situation in which actually we have divergence. So the learning rate is crucial. If it is too small, of course we will have a huge number of steps, but if it is too large, we also diverge. So the next time I will look into a few of the improvements. I want to basically explain how the very famous Adam optimizer works, so with a couple of tweaks on the basic steepest descent. Yeah, but I stop here for today. Thank you.